which is Ziyu Huang, who's speaking about molecular dynamics simulations of water and hydrogen formation on the lunar surface.
Thank you. Can you hear me?
Yes, we can hear you.
All right.
And we can see you.
Okay, how about the slide?
Perfect.
Okay, thank you. Okay, good morning. I'm Ziyu Huang. I'm a second-year PhD student at University of Southern California, and I work with Professor Joseph Wang. And this work is also collaborative with Professor Nomura and Professor Nakano from USC. And today I'll be talking about molecular dynamic simulations of water and hydrogen formation on lunar surface as induced by deep dielectric charging. Okay, so first I would like to give a brief introduction about water, hydroxyl, and hydrogen observations. Several observations has been made to map water distribution on polar region, and they have already detected water concentration in craters and craters in polar region, and also permanently shadowed regions. And land from ARO also detected high rich hydrogen in those areas. But one of the reasons is very obvious, which is temperature. So PSR has temperature lower than 40 Kelvin, which can keep the water in ice or frost. So however, the source of water molecules are still under debate. So here are some theories and experiments to model the formation of water molecules. The mechanism of slowing interactions is the implanted protons combine with oxygen to produce hydroxyl, and then the diffusion of hydrogen can combine with other hydrogen to form H2 and then being released. And the hydroxide inside the regulus can also trigger recombinative disruption as the picture shown on the right, which is from John's paper. And however, to get recombinative disruption, it requires enough energy, like a high temperature. And protons implantation alone is not enough to generate water and liberate water. So Drew et al. Did an experiment to model micrometeorite impacts. The heat released by micrometeorite impact would be enough to generate water, but scientists think like how about some other sources which occurs more globally and not limited to just one location. Then I started to think again, the contribution of solar plasma. And one of the interesting thing I found is when I was reading Jordan's paper about the dielectric breakdown. The figure on the right is the probability of deep dielectric breakdown, and on the left is the estimated electric field induced by deep dielectric charging. The electric field is in the level of 10 to the 6 voltage per meter, which might be able to cause some water formation reactions just like micrometeorite impact. And also the rate concentrated at permanent shadow regions as a function of time. And by the way, it's reasonable to estimate the electric field to be several times stronger due to the irregular shape of regulus and some more extreme solar energetic particles events. So I decided to use molecular dynamics simulation to test this hypothesis, to test the silica nanoparticles with hydrogen surrounded. So something about our model, we use RxMD to do the simulation. RxMD is developed and actually still being developed by one of our co-authors, Dr. Nomura. The code includes a React FF force field and polarizable charge equilibration model to better solve the effects of electric field and also chemical reactions. We use silica as silica O2 to represent dust particles. Actually, we wanted to use some other lunar simulant like olivine, but it's really hard to find like the force field since iron is so reactive. The electric field is chosen as 5 times 10 to the 6 voltage per meter, which can be found in Jordan's paper. So first we tested 2 cases, both with the same setup, and one of them is completely without electric field, and we call it simulation 1, and the other one is the case with an electric field, which is simulation 2A. And then we plotted the time history of number of water molecules as silica O4 tetrahedral and also hydroxy group. Case 2A had a significant amount of water generated, and the silica was melted down, as we can see from the number of silica. For hydroxy groups, case 1 doesn't change, which means the hydroxy just stay on the surface and no reaction occurs under the temperature. Case 2A, however, has less hydroxyl groups than case 1, so that means hydroxyl are combined to form water molecules. So, and after that, continued from simulation 2A when the fragmentation rate.
Did we lose them?
Yeah,
Or is
it's
it
actually stuck on my screen as well.
okay. We could go on to the next talk and have him finish up at the end, or why don't we wait 30 more seconds, see if he can dial back in.
Sounds good.
I will go over this really quick. So basically, we're trying to use deep dielectric charging events to obtain a really high electric field, and we want to explain some water formation process based on this electric field. So I believe that's where I left. We set up a molecular dynamic simulation like this, and then so this is we tested two cases, both with the same setup, and one of them is completely without electric field, and we call it simulation 1. And another one is with an electric field of 5 times 10 to the 6 voltage per meter, and that's simulation 2A. And we plotted the time history of the number of water molecules, silica 4 tetrahedra and hydroxide group. And case 2A has a significant amount of water generated, and the silica was melted down, as we can see from the number of tetrahedra. And for hydroxide groups, case 1 doesn't change too much, which means the hydroxide just stay on the surface and no reactions occur under that temperature. And case 2A, however, has less hydroxy groups than case 1. So that means hydroxy are combined to form water molecules. So after that, continue from simulation 2A. When the fragmentation rate of the system reaches the highest value, we shut down the electric field and relax the system to 40 Kelvin as case 1. So that represents the end of a deep dielectric charging event. And the system was cooled down by heat conduction from outer system. So that's actually the video. So the connecting energy of the atoms, of all the atoms, turn into potential energy by forming bonds. And finally, the temperature was relaxed to the original temperature, and the final structure was obtained as figure C. So now let's take a look at the time history of molecular numbers. So simulation 2A, it was actually shown before. So after we shut down the electric field, the silica tetrahedral numbers grows, which means the regular structure was preformed as it used to be, and the water molecule number, total water molecule number decreases a little bit, basically due to the trapping inside the silica structure. And there are a lot of water molecules attached to the silica surface, and there were like hydrogen bonds and other bonds formed. So we also found some ice structure as shown in figure C. So one of the interesting features we got from this simulation is that fully hydroxylated silica surface is believed to be hydrophobic. And our simulation just shows that the reactions turning reduce the number of hydroxy groups and water molecules are attached to the surface. So that potentially means the deep dielectric charging breakdown leads to the change of hydrophobicity of the surface. Well, this could be a key feature for lunar regulus, basically because that would tell us whether the regulus is able to deposit water or lose water. So later we did another simulation to reapply the electric field to the structure we got from simulation 2B. And once we apply the electric field again, we can see some hydrogen and water molecule released. So we started to think that for larger systems, if the volatiles are released from the regulus, then maybe we can see the porous dust particle structure. Another interesting finding from another simulation is that when we shoot hydrogen atoms from the top of the surface, hydrogen ions are captured. Hydrogen ions are also a carrier of water molecules. So if more in-situ measurement data can confirm these ions, then the charging potential of lunar surface might also be a factor for lunar water transportation, like from lower latitude to polar region, and also from day side to night side. So to conclude the work, a new hypothesis is proposed for water formation at the lunar surface, and it was simulated by molecular dynamics. We found that hydrogen from solar wind interact with regulus to form water, and with an estimation of 3,500 years of implantation, more than 15% of the oxygen from the regulus becomes water. And also hydrogen ions are also captured, which could potentially become an important factor in lunar water transportation. And also the change of hydrophobicity could be another outcome of space weathering and deep dielectric charging. But anyway, the electric field from space weather may be a key factor in the water formation process. So, and with that, I will take any question you may have. Thank you.
Very interesting talk. Sorry, it got interrupted halfway through. That's unfortunate.
Yeah, apologies for that.
We got you in time anyway. Are there any? I see a hand is up. Micah, you want to go ahead and ask your question?
Ziyu, this is a really interesting talk. I agree with Carl here. One thing that I noticed, and I recognize that these are probably early results for you, but how do you explain the fact that no experimental measurements have ever seen the formation of water molecules, while your simulations do?
So I'm sorry. What was that question? Like, for the measurement.
There's a lot of experiments that have been done on silicate, SiO2, implanting with hydrogen, and pretty conclusively showed that no water was formed. But you appear to be showing that a lot of water is formed. So looks like maybe you froze again. Uh-oh.
Oh, that's too bad. Are you there? Now, his models assumed cold temperature, weren't they? Because he was using dielectric breakdown, which requires for that resistance to be large. Regolith needs to be cold. So I understood his talk. Well, that was actually going to be my question. Is what temperature does this occur at?
Gotcha.
Yeah.
Sorry, could you hear me now? Use another device. Great. Oh, I'm so sorry for the power outage. And could you, if you can, could you repeat the question again? I didn't catch that.
Oh, my question had to do with the formation of water molecules, and if you can explain why you see them in your model, but they haven't been seen in experiments.
I think there should be some experiment, like I mentioned before. There's, I think there's a group in Hawaii did some micrometeorite impact to produce some to produce some energy for the fully hydroxide lunar simulant, and then water formation was detected by this kind of mechanism. But I don't think anyone have this have done this kind of dielectric breakdown experiment. So that's kind of something we are interested in the future. Maybe we will test this in our lab, or maybe looking for some in-situ measurement data when the space weather is really extreme condition in the polar region. So maybe that could be a verification for a model in the future.
I got you. I understand now. This isn't due to hydrogen implantation or irradiation. This is dielectric breakdown of saturated soil.
Yeah, that's right. Sorry, I didn't show that in before.
No, I got you. Thank you. That's very interesting.
Thank you. Thanks so much. And let's see. Pam Clark mentioned everybody that there's a group. Okay, she confirmed what you were just saying.
Yes, I noted that experiment with great interest. It came out, results started to come out about a year ago or so, perhaps. And they were the first group, I believe, that added in the thermal bit from simulating micrometeorite impact. There's still a lot of work to be done, but it was a very interesting result.
Yeah, that's the paper I was talking about. It is the use of like micrometer impact, a lab to simulate the micrometer impact. That was really good.
One last point by Jeff Gillis Davis is that you're basically, the difference is you're doing this through dielectric breakdown instead of irradiation with the laser. Different process.
Yeah.
What temperature does the soil need to be at for a dielectric breakdown to occur or be effective for causing this? Is that part of your model?
So basically, I think from a model, from our molecular dynamic model, I see the temperature can go up to like over 1,000 Kelvin, and then but immediately, like in femtosecond, they were relaxed into like 40 Kelvin, which is the environment temperature on lunar polar region.
Okay.
So the reaction actually happens in a really fast period, and then it will relax to the original temperature.
I see the point. Okay. Thank you.